Anyway, who here has ever heard about ECS or entity component systems? Okay, not even a half, I would say. I'm bad at math. Let's get it out immediately out of. I'm not a good math person, but that was roughly half for the camera, and maybe a bit less than that. So that's good. That's my audience. We're gonna learn together what it is about and what learnings we can take from it. I'm not trying to sell you an ECS. I think maybe I'm getting ahead of myself a bit. I'm not trying to sell you an ECS, but I'm gonna explain a bit what it is, why did the concept come to exist, and what you can take home. Even if it's not really a thing you can entirely use. So, if you ever been to like any game developer conference ever, this is like if you ever get a bingo card, this is the joker. This is the one that always wins, because regardless of the talk, one of the first 3 comments would be, by the way, have you thought of using an ECS? That would solve all your problems, regardless of the talk. You can talk about animation, audio, design, doesn't matter. Use an ECS, it will solve all your problems. That used to be the talk, like every time I watched a GDC talk, that was guaranteed top 3 questions. And I tried to do some Google Trend search just to see. You can see there was a big spike somewhere in like 2017, 2018, and then the hype kind of died down. And then it's still backing up, but I don't know charts much. I don't really offer financial advice, but it does look like it might be going down again. We'll see. And also a bonus, apparently Sweden is leading the chart, so yeah, go Sverige. I live in Sweden. I don't speak Swedish, but it felt good. I don't know why Sweden is like 100% on ECS. That's not entirely my experience, but who knows. Anyway, hi, I'm Mathieu. I'm a tech lead at the Paradox Development Studio, where I work on Hearts of Iron and other stuff that I cannot talk about, or else I'll be fired. But yeah, it's a video game company. We make historical video games. You may have heard about us. So this was a very difficult talk to work for me, because I knew over summer I wanted to talk about, usually I talk about what I've researched the year before. That's how I go for conferences. And I wanted to talk about that exploration about data-oriented design and a bunch of things related, but I couldn't really get the talk out. So what I did is I went to my meetup and I said, hey, I have a talk about ECS, but I don't really know if it's about ECS. Please come at the end and tell me what this is about. I didn't get the feedback I hoped, but I got a really good idea in my shower like 4 days ago, so I rewrote half of my slides, and I hope this has a better connection to the thing. If you've ever seen, actually, maybe another appreciation. Has anyone of you seen one of my talks before? Oh, I have some fans. Nice. Well, okay. For the camera, that was everybody in the room, by the way. Thank you. Okay, so I made a talk about profiling, I think like a year ago. I made one about multi-threading 2 years ago, also based on my games. One day I think I will have to talk about allocations. But the thing that I keep running around is basically it's performance related. And it's usually things that I realize are bad for performance in the games I work on, and how do I try to bring after I solve some issues or I notice some issues with that, or fix some problems, how do I bring back that knowledge? And I think this is really the work, the thread through all those talks. Like, how can you profile your performance problems, and then how can you use threads? How can you fix your location, which won't happen one day? And today we're going to talk about caches, data locality, and how those RAM work, basically. That's going to be our goal. So we're going to talk about what is ECS, or entity component systems. You'll probably be like tired to death of hearing the words ECS by the end of this talk. I'm warning you in advance. We will talk about data-oriented design, which I think is going to be maybe the meat of this talk. And in general, cache-friendly data structure, and what does that mean? And coupling, or more importantly, decoupling your code. And you'll see there is a very strong connection to some degree between data-oriented design and like thread-friendly design. But first, let's talk about hardware, because this is a C++ conference. We really like to talk about hardware. We like to say that we're very close to the metal to some degree. So let's thought about that. We can start by giving some appreciation for the people who make the CPUs that make our job exist. First, we can eat, and two, they're actually pretty good at what they do. Like, I don't know if you ever looked at like the actual raw numbers of how much stuff your CPU can do on a daily, on a nanosecond basis. It is crazy. Like, most basic arithmetic is like a couple cycles, and again, I'm not a physician, but from what I'm told, like a cycle is like you divide the one by the frequency. So like if you have 4 gigahertz, that's about like something less than a nanosecond, which is just an amount of time I just can't really represent in my head. I'm told the best way to figure out the speed of light is to use like how much, to figure out nanoseconds is to figure out how fast the light can go in a nanosecond to give you like a reasonable physical distance that you can make your head about. It's nothing. Like a nanosecond is nothing. Again, your CPU can do 4 billions of those in your CPU has 4 gigahertz, does 4 billion of those things in a second. That's an insane amount. When I was in school, I was taught to avoid divisions and square roots in code because that's really bad and your CPU can't handle that. I'm not saying it's a lie because it is technically way slower by maybe like a factor of 5 or 10 than making an addition or subtraction, but it's still nothing. Like again, a few dozen cycles, again, at 4 gigahertz, your CPU can crunch like maybe not a billion of those, but probably hundreds of millions of those per second. I don't know how many numbers you need to divide, but I don't think that's gonna be your performance bottleneck. And then if you have SIMD, and every CPU for 20 years I've had SIMD, you can multiply that by 4 or 8, depending on how many levels of AVX and NSSC instructions you have available. It is absolutely insane, and that's really the bit where I like, the CPUs we have are really stupidly insane. And I think that's been a big thread through the talks I've been having lately. It's a simple but very important realization that none of what we do should take that much time given how fast those things are. And yet, well, we all have performance problems. I mean, I don't know, who doesn't have performance problems? Okay, I'm not lying, this is nobody in the room. Everybody thinks like, maybe they could get a bit faster if they could. So here's the problem. Here is one of the problems. That's the problem we're gonna focus on today. The problem is memory, right? Because there's this thing called physics, which I'm about as good at as with math, but it says that you can only go so fast so if things are too far away. So basically your CPU is very fast as long as whatever data it needs to read, like those bits, are physically close to it. And by physically close, I don't mean in the same room or even in the same computer. It has to be on the chip. If it's not on the chip, it has to figure it out another way. So basically what I mean is if it's in the RAM, you're out of luck. Like if it's in your CPU registers or in your L1 cache, which are like data storage on your CPU, then you're fine. It's faster. It's collocated so it can operate at the same frequency as the CPU. But if it's not, if it's somewhere in your RAM sticks, and don't even get me started, or if it's on disk or on a machine on the other side of the world, like that, we are not even talking about that today. We're talking about like if it's in your RAM stick instead of your CPU, it's too far away. And I have a couple of slides to explain exactly how much, because I don't think it's always easy to grasp. So here's a very accurate representation of a CPU and some RAM sticks. It's about 100 nanoseconds, roughly speaking, and as far as I know, that number has not really changed in the past 10 years. I mean, they tried to do some stuff with like CLS, like super gamer RAM, but I mean, roughly speaking, 100 nanoseconds, if you need to actually fetch some data from one of those like tiny chips and put it in this chip to scale, or not. I don't think it's to scale at all. So 100 nanoseconds. Okay, but again, what's a nanosecond? We talked about that before. That's a very hard number to reason about for most people. Like I start complaining when it takes a couple seconds for an application to do a thing, and probably if it doesn't respond in the second, I get angry. But 100 nanoseconds, I don't think anybody can measure that in their head. Like that's just physically impossible for us. But as we said before, it's like it's 100 cycle at 1 gigahertz. So already we start having like a frame of reference. Assuming your CPU is running at 1 gigahertz, it's not, right? It runs at like 2, 3, 4 gigahertz, 5 if you have turbo. But for an order of magnitude, it's good enough. If one arithmetic operation is like one cycle, so 1 nanoseconds, well, fetching the same data from RAM is 100 nanoseconds. So it's 100 times slower to fetch the data, do the addition, and then push it back to whatever memory cell you have, than to add it. Like if you have to fetch it, add it, and then push it back, it's going to take you about 200 nanoseconds to do the round trip and 1 nanoseconds for the addition. You're like, you're wasting your time. You're basically, the arithmetic doesn't matter. What operation you're doing doesn't matter. What matters is how fast it can get to your machine. And to really hammer the point, I want to compare that with like the other caches we have on your on a modern computer. So if it's on a register, it's usually considered free. Like it's basically as part of your operation that does like an add, a multiply, whatever other arithmetic your CPU does. Writing or reading, it's just free. It doesn't really have a measurable impact. If it's in your level 1 cache, which is also on the chip, about half a nanosecond, you can measure it. It is technically not free, but it's as close to 3 as it can get. If it's in your L2 cache, then you start being a bit slower. It's 4 nanoseconds, but still, like those numbers, especially if you start normalizing them, like assuming that an L1 cache hit is 1, it's a matter of it's times 8 and time 200. And to really make sure you understand this, I'm gonna show you a small animation that I saw in another talk and painfully recreated in Google Slides because it's. I'll see. Okay, so I'll try to scale to show you the time to fetch. So let's do L1. Woof, that's done. You barely had the time to blink. Okay, let's fetch for L2 cache with the same like time scale. Okay, let's do it. Okay, well, I could see it going, right? So it's not as fast, but still, I mean, if we compare it, like, okay, this is instantaneous, and this is close enough. All right, let's fetch from RAM now. I can take a drink. Almost halfway there. Wait, you almost got it. You're almost gonna be able to increment that pointer by 4. Almost. Almost. There we go. And now we can dereference it and do it all over again because it's another part of the memory. Cool. So I think you get my message, right? Memory access is slow. It is stupidly slow compared to what your CPU is able to do. And it's basically bottlenecking a lot of things if you get in the wrong situation. It's really bad. And that's why engineers have spent the last 20, 30 years making a lot of cache. Every time you see a CPU now, it's a big argument how big the cache is. And this is the reason. It's because L1, L2, L3 caches are trying to basically hide that latency from you by trying to get the data or keep the data around to help you. But there are limitations, and that's what I want to explain a bit. This is what we call data locality, and that's what I will explain, okay? So your caches, like let's just say you have an L1 cache and it has a bunch of lines. I think each L1 cache is about 64 bytes. It's not a lot, but you have a bunch of those. I can't remember the size off the top of my head, but you have a bunch of those. And the idea is, every time you try to read some data in memory, the CPU is not gonna just fetch the 2 bits or the not bits, but bytes. Like if you ask like to read like an int, 4 bytes, it's gonna be nice with you. It's not gonna just fetch those 4 bytes because that would be super wasteful. It's gonna fetch those 4 bytes and everything around it, like on a 64 byte segment, basically. The reason is, well, first of all, it's just throughput. Like if you can't beat the latency, try to beat it by just sending more data, because maybe you can just have more stuff going on your bus. So that's the first thing. And the other one is just usually or possibly when you access a bit of data, there's a high or reasonably high chance that the next bit you will try to access is basically the one next to it, which means it's already there. We already paid the cost. Might as well do it, right? And that's what caches do, right? So if I keep reading my memory cell, assuming it's an array, for example, like I have an array of ints in memory and I try to iterate from it, that's what it would do, right? I would just go through memory and I would just read them all the time. The first one I will pay for because I have to fetch, but all the other ones are virtually free because I already pre-fetched every line immediately. And your CPU founders are also really smart. So what they realize is that if you keep, walking through memory like 1, 2, 3, 4, there's a high chance that it's going to continue, right? Patterns have these things. So we have there's a mechanism called the prefetch. We will automatically realize like, hey, you keep hitting those memory addresses in a sequence. You know what? I'm going to save you from yourself. I'm going to prefetch the next one. Because so by the time you're at the end of that one, you're probably going to have this one already loaded. It's very nice. And they're smart enough to realize that, if you can plus plus, you can minus minus. That's usually like the 2 ways people go about arrays. So if you go the other way, at some point they will also do the same thing and fetch the top one. I'm sorry, the color doesn't really show that much, but what I mean is that, yeah, this line is now also loaded by the time you reach the end. So even if you're going like decrement, you will get there. So every time a colleague tries to have an argument with you that, going incrementally or decrementally through an array changes thing, it doesn't. It's roughly the same thing. The CPU people have figured out that you can go 2 directions with basic arithmetic, and both directions have a prefetch mechanics. No matter, it works fine, and it's really good. So basically, memory access is slow. We've been that, but caches will try to alleviate most of that by making sure that the minute you start accessing some data somewhere in memory, it will basically load the rest around it, and then if you continue growing or decrementing addresses, it will continue doing the same pattern, and most of the time the data will be ready for you before you actually need it. Roughly speaking, if it can predict the thing. But again, it has to be able to predict the pattern, And it's smart, but it's not that smart. So it can predict that after 1 comes 2 and after 2 comes 3 and the other way around. That's the two fits it can do. But if then you jump like plus 10, minus 5, 42, and then completely over somewhere in the memory, then you're out of luck. Then it can't predict where your next memory load will be, so it can't prefetch it for you. So you're going to be looking at the loading animation that I showed you earlier. So if I have to summarize it the most like stupid way possible, it really is linear access good, random access bad. Or like, if you go up or you go down, you're fine. If you do anything else, and it doesn't really matter if you jump 100 or like 1,000,000 memory cells, it's kind of roughly the same thing, you will have the same problem. You will hit the problem that this memory is not really available on your cache, and it's going to have to fetch it first. And this is basically the whole reason why there has been a push for this thing called data-oriented designs. It's not that new. As far as I know, people have been talking about it since like the early 2000s, at least. And the words ECS, Entity Component System, have also been mentioned somewhere in the 2000s. But I know it's making a comeback, and I think it might potentially be related to the fact that, again, we're hitting a bit where we can make the CPUs as fast as we want, but the RAM stacks have been as fast as they are for like 10 years and have not really changed. So this is getting a bigger, I don't know if it's a bigger deal, but it's still a big deal. It's not going anywhere. So the point of data-oriented design is to try to work with the CPU rather than against the CPU, and basing, okay, your CPU is good at arrays. That's what it's good at. It sucks at math. It sucks at maps. It sucks at lists. It sucks at anything that jumps randomly in memory. What it's really good at is for I equals 0, I less than size, plus I. It's really, really, really good at that. And if you have to bulk process anything, it's going to be very good if you do that with a vector. It's going to be horrible if you do that with anything else, or anything else that is not linear access memory. You might get away with a deck if your chunks of a deck are big enough. But if you start going with a list, a map, or even an ordered map, especially the standard ordered map, you're not going to have a good time. So the idea is that, okay, we try to think about bulk. Because again, when you program, you should usually optimize for the bulk case, not the one case, right? Okay, if you have to process a transaction, it's a transaction. But that's usually not the thing that kills your performance. The thing is when you have to process 100 of them. And I know as programmers, especially the way I was taught, and I think it's still a thing, we try to think of the one case and then, okay, I can generalize it by putting it in a loop and calling the same function. That's a very normal way of modeling things in your head, right? Like you do the one case and then you write a loop that just calls this thing repeatedly, which works, but the idea is to try to go away from that and say the one case is the exception. It's not the one I care about. The one I care about is I have X amount of data and I will process them in a bulk. And you don't have to write it as a loop with no like function in between. But the rough idea is that's how you should think about it. It's really I want to do a bulk processing, and I want to do a bulk processing that just takes an array in and outputs an array out, or uses the same array. Both options are correct. And to show you an example, this is usually called as the array of struct versus struct of array debate, or fight, or conundrum, whatever you want to call it. So, okay, let's say we make a video game, right? A very simple video game. We have a thing called a unit. I make strategy games, right? So you have like units on the map, like they're little dudes with guns and tanks, and they just move around. So it's maybe the simplest possible thing. It has a position, a velocity, and some HP. So position is free float, because we're doing 3D, so you need free coordinates. And it has a velocity, which, again, like one of them is probably 0, because your tank is usually not flying up. But let's just say we want to handle every case, so we don't bother. That's the thing. It's free floats again. And finally, I have an int, which is my HP, and if I run below 0, I die, and the unit is gone. That's very, very basic, like the dumbest possible thing I can do. The classic way you would do it, in most like way you want to think about it, it's like, okay, that's what a unit is, right? A unit is described by its position, its velocity of its HP, so I chug all of those in a struct, and then what is my game about? My game is about a vector of all those units. That does make some kind of sense when you think about it. Like conceptually, if you start trying to explain the design of your game, it does make a lot of sense. Sadly, your CPU hates you when you do that, and you very much prefer the one on the right, which is, okay, we don't have a struct for a unit, we have a struct for all the units, and what is it? It's a vector of positions a vector of velocities, and a vector of HPs. And then at the end, all units is, well, it's just, it's a struct of one item. And why would we do that? Let's look at what it is. Like, let's look at the memory layout of our thing. Let's see, we have like a classic array of structs. So this is my memory. This is, I think each cell on all of my slides is considered 4 bytes because floats and ints are 4 bytes. So this is my unit, right? It's 4, 8, 12 bytes of position, 12 bytes of velocity, and an extra 4 bytes at the end for HP, which is an int. We don't have any extra alignment requirements, so we can even just call them, put them side by side, and there is no padding or anything. Let's exclude padding from the equation right now. It's just, that's our unit, that's how it would be laid out in memory, and and so if I have a lot of them, they would do that, right? Like you would have the first one here, the second one here, etc., and they would just be laid out in memory like that in my vector. That's reasonably what you would do. But now let's look at what the operation I actually try to do on those units do. It is very unlikely that I would have one, or it would be probably bad design, even from a simple single responsibility principle concept, that I have one function that does update the thing that does everything in one go, right? I give it a unit and it does everything. It draws it, it updates its position, it simulates combat, it is the one function. That's usually not how you would structure something. You would have like several systems in your game that are possibly managed by different people, or maybe at least written at different time, or maybe run on different schedules, and they would each access a part of the actual data. So for example, I have a bit that updates the position of my unit, which I'm really bad at math, but I'm told it's just a sum of those two, because if you sum your position and your velocity, you have your new position. And you can multiply by a delta if you have time, but that's the rough idea. So basically what we do is that we use those three here, and we output those three here. That's basically the memory footprint and data footprint of our function. Then I have a thing that will just simulate damage because I have a combat system somewhere, and the only thing it will access is the HP data member, and it will probably change it. And then I have a third system, which is my 3D graphic thing that is just rendering all my stuff on the screen, and it doesn't care about any of that. The only thing it cares about is the free coordinate, so you can put it on the screen and see if it's visible for the player or not, which is some math involved. And it only cares about those 3 bits. Now here's the thing. If I try to update position, I will try to keep every time like in gray all the bits that you don't actually read but still have to fetch because you're reading this data from memory, right? And all those things come together. So in a classic like layout, if I have my update position, it's not too bad. Like out of 7 quad bytes memory cells, there's only one that I don't care about when I iterate through the array to update the positions. So, 1 in 7 waste, it's not the best. But I've seen worse, right? As far as waste is concerned, it's potentially an acceptable trade-off. If that was the only case I had, I would say maybe it's not worth changing all my code just to get that benefit. Whatever, it's fine. But then we start having a function that just simulates damage, and now we're like, oh, I only use 1 in 7 cells of memory. And again, memory fetches are expensive, and even if you can try to prefetch, the more packed it is, the more likely your prefetch will actually give you all the data you want, because even if you prefetch, it still takes time. So if in the time the prefetcher run, the only thing you had is like touching one end, it's very likely that the next bit you will need will not be ready and you will be waiting on the memory bus. So that starts to be a problem because for every 7 quad bytes I fetch, I use 1. And the 6 over are just wasted. I don't care about that data. It's just there to take space in the memory bus. So I'm wasting a lot of bandwidth, and we don't like to waste bandwidth when we're talking about performance. And then when I start running my renderer, I have the same issue. It only cares about the 3 first quads of every structure, and then the rest are just garbage. Like those bytes could be random for all it cares. It's never going to read them. So same thing. I'm wasting about over half of the memory fetches I do are useless, and I could just do without them and roughly be twice as fast. That's a bad estimation, but I have some benchmark later. So, what if I do the opposite? What if I have a vector of position, a vector of velocities, and a vector of hit points for every unit? I guess I should have like maybe split those, because you can see that there's way more units stored in this one than in those two at the top. But that's roughly the idea, right? This vector is like 3 times smaller in memory due to the sizes. But if I start doing the same update thing, well, this time The green bit and the gray bit is the bits I don't fetch, but it's fine because I don't use them. So while I will run this update, I will have like my memory bandwidth will fetch this this position, this bit in memory too, but it will never fetch those ones. So everything I fetch is exactly what I need. I waste zero memory on the process. And your caches are smart enough that you can have several independent arrays in your cache at the same time, even if they share like some similar modulo memory addresses. There's a thing called associativity. If you ever look at the specs of your CPU, it will say like X cache associative. Like I think the minimum nowadays is 4, which is like if you have 4, if you try to fetch 4 pointers that happens to line on the same cache line, you still manage to have the 4 and they don't eject each other. And on like big super modern CPUs like the top like Intel or AMD CPU you get, I think you have like 12 lines or something ridiculous like that. So you're not going to have a problem with that. If I look at hit points, it's probably the best I can ever do. I'm just fetching a vector of ends and I'm just iterating through it. And I will never bother reading the last one. And same thing for the random thing. I will only read my positions all the time. And again, all of those operations waste zero memory. They always only read what they need. And again, that's the thing we're trying to optimize. It's the amount of memory we fetch because that's our bottleneck. So what we call data-oriented transforms is basically the idea that you make small loops that operate on an array of fields. And those fields in the arrays are only what they need and exactly what they need and nothing else, or as close as nothing else as they can. There is an upper bound to this process because if you push this process far enough, then every field is just one int or one bool or whatever. At some point you start maybe thinking, you know what, it makes no sense to have 2 arrays of those things. Maybe they should be in the same array because they make significant sense to be together even if half the transform maybe you're not using all the data. But as far as possible, what we're trying to do is make sure that we have small loops that operate exactly on arrays of fields they need and only what they need. So you minimize the amount of data in the cache that isn't read or write during the update because again, cache sizes are very, very precious. If you ever look at the spec sheet of your CPU, I think you have like, even on a very expensive CPU, your L1 cache is like 64K, I think, 108K maybe. That's not much compared to like the, I don't know, 12, 16, 32 gigs of RAM you will have. So you really try to optimize that real estate. And that's the bonus that I will make a small side note about is those transforms. Then you realize, wait a minute, those fields that I'm looking at, like they're entirely independent. Like you know, this step uses only those bits. This step only uses those bits. I could even run them at the same time on 2 different threads, and I would not need any synchronization because I'm guaranteed by construction that they're literally not accessing the same data, the same data fields. And I think we had a talk earlier today about like data synchronization. I couldn't make it, but one of the big things you have to know is the best way to do data synchronization is to not have data dependencies. And then you don't need any atomic or mutexes or whatever. You can just prove by construction that those 2 threads can run at the same time. And another way to optimize CPUs that have been working a lot for the past 10 years has been adding more cores. So, all right, let's look real quick at a benchmark. So far, it doesn't look that big of a deal. I made a small benchmark on QuickBench, which is just I created like, I don't know, 100,000 units, and I run the 3 updates in sequence. And this is what it got, what you get when you do it with an array of structs, and this is what you do if you have like a bunch of a struct full of arrays. It's not, I mean, it's like a maybe 10, 20%. It's not non-negligible, but it doesn't sound like a big deal. I will get back to that. But first, this is the small break I have to talk about code architecture. Because this is the bit about coupling that I think is important to keep in mind after talking about caches. Because, you know, we're not only just wasting memory when we start having like cache line full of data that an operation doesn't need. We're also mixing up concerns. Because to some degree, I think it hinders maintainability that a struct has a lot of fields that are technically not used in the same update, even if logically they make sense in your like mental model. Like you know, if you're trying to design a unit, you say, okay, a unit is a position, a velocity, and some HP. But when you're thinking about code and what data do those functions actually need to access, then you realize that it's really hard to reason about because in the first model, my random method takes a unit as a parameter. I cannot, like, unless I look at the implementation of the random method, I cannot guarantee that it will not read any and all fields in the unit, and then I don't know if two operations on a given unit are thread safe, for example, and it's just a lot of cognitive load because there's all those fields that are given to me in my code, and it turns out I only care about one. So basically, it's a thing that we've cautioned people against, like coupling and mixing things together forever. I think as far as we taught computer science, we say, don't mix concerns that don't need to be mixed. And usually when we think about that, we think about code, right? We say, okay, this function should have only one responsibility. But I think it should, and I don't think it's a thing I invented. I'm pretty sure it's a thing that's being taught more and more. You should also apply that to data. Why do you have a struct that have members that do not appear in the same update? Well, then maybe they shouldn't be the same update. They should maybe be two different structs. And then you could have like a parent that is the same, and they could both have the same index in two different arrays, but they're not the same, and they don't have a reason to live together if you don't actually use them together. And again, the point of data-oriented is to look at, like, the architecture comes from where the data, of how the data is accessed, and not how the conceptual model in our head looks like. So yeah, basically, don't mix fields that are not accessed by the same function. It's all or nothing, right? Like if I take an object as a parameter or a collection of objects as a parameter, the default, if I'm reading the code, is to assume that they can access anything. So the least I give them, the better, because the more assumption I can make. And as I mentioned, then I can, I can't reason about data sharing. If I have two functions that takes like writing a mutable copy of a mutable reference to a unit, I can't assume that they're both able to run at the same time. I can try to read the code of both functions, prove, as in my head, convince myself that it's safe, then decide to put them both in a different thread to gain performance, and then a developer comes back and doesn't know about this thing because, I mean, he's given a function that is allowed to access all the unit, and then starts creating a data race. And I can't enforce that in code because it's one struct, and either I lock it for either I lock it and then it's not multi-threaded anymore, or I don't lock it and I pray to God that nobody violates the promise. So yeah, if you remember that talk, I don't know if you've seen it. It's pretty good. You should take a look at it. The idea is like, yeah, you can't be thread safe if you use two functions that takes mutable references to the same thing. So if you split the object in smaller parts, then you can prove, like by reading the code, that those two functions literally do not access the same data member. Ergo, they are thread safe. And if you decouple your data, well, first your buffer, your memory will thank you, but also you will have a way easier ability to decide if those things can be thread safe, if they need to be saved together. A lot of good things come from here. And now we can go back to our benchmarks. So, because I only had 20%, right, in my previous benchmark about the difference between the two, which sounds nice, but I can understand why someone would come to me and say, Matthew, like, I'm not rewriting my entire like unit class and everything that accesses it just to gain 10%. Like, 10% is nice, but it's not worth it. And that's a fair argument. I would accept it. But now, this was a minimalistic unit, right? This is not an actual unit in the game. An actual unit in the game, I'm just going to put some padding data to simulate it. But an actual unit in the game, in my game, would have way more data than this. It would probably have like a bunch of other stats and not just HP. Probably like some data concerning like which models and texture it should use. Who's the owner? Million other things you can imagine a simulation is doing to simulate an actual like unit. And if it's a tank, like maybe you have data for different parts, like is the cannon damage, did it lose a track, how much fuel does it still have? You can go as far as you want, and we make very complex simulations that people really like having millions of stats per unit. So that gets really quickly like an issue. So they start to be a bit more fair. So assume that instead of like no data here, there's maybe 32 bytes of like extra stuff that I also don't need in my updates. And now it starts starting to be a bit more like, you can see the difference, like it's very noticeable. It's almost twice as fast. If we start going to 64 bytes extra padding, it is over two times as fast. And if I go to 128 bytes of extra data that I don't need for my updates, you can start getting to, I don't know, like 3 times, maybe 4 times. I stopped here. I could have continued. It gets worse. The good thing is at some point it stops. It stops because there is a limit, and the limit is for each unit you basically need to fetch the memory and wait. And that's the worst you can do, which is bad, but it has an upper bound, which is an upper bound that your code probably has on some systems, because mine has, so I'm assuming other people have the same. There is an upper bound, and it's not obvious that there is an upper bound, but when you change your code, you suddenly realize that, wow, the same exact code could run like 8 or 10 times faster just because suddenly the memory access is actually efficient. Which brings us to the concept of ECS and why do people talk about ECS? I know it took a while to get there, but we're finally going to start talking about what is ECS. And again, it's because the main point of this talk is not as much ECS, but more like why are people talking about ECS and what can you learn from it? Because as we will see, it's somewhat of a fad, but there is some interesting idea behind that. So the idea of ECS is that we bundle fields into components. So like, for example, all my position would be a component, which is like free floats. Velocity would be a component. HP would be a component. I have another slide to explain it, I think. Then every object in the world is an entity, which has a unique ID. I mean, classically from 0 to like how many you have. But that's you could do different models of ID, but some form of a unique identifier that allows me to look it up if I need to. And then each entity can have an arbitrary number of components. So like not every entity in the world will have a position, a velocity, HP, and the 20 over million components that you can think about in your game. So like, you know, like does it have like a stockpile? Does it have like a fuel reserve? Does it have like an owner? All those could be considered separate components, basically. And you can add or remove components through to a given entity at a given point. For example, like if a unit is under construction, maybe it has like a construction progress thing, but it doesn't have an actual like effective stat because it's not done. And when it's done, then you transform it and you say, okay, remove the construction component because it's been built and give it like an actual active role component instead, things like that. The other classic is an AI component. Like if you have a tank in the game, as long as the player controls it, for example, you don't need any special data for it. But if it's not controlled by the player, but it's controlled by an AI, then maybe it has an AI component with all the data that the AI needs to simulate and make it move. Things like that. And then what is a system? Well, a system is a transform, basically, that operates on a selection of components. So I will explain that. So yeah. And then the big concept is like if you want to update the world, what you do is that you gather all the entities in the world. Then for each transforms, you say, okay, give me all the entities that satisfy all the components I need as input and output. And then I do a ball transform on those. And potentially, from framework magic, I can realize that those transforms that do not use the same components can run at the same time through like some scheduler mechanism, basically. That's the base idea. So if we go back to a very minimalistic game design here, so this would be like our transform or like update position, take damage, and renders are basically our transforms. Our components are position, velocity, and HP. Each one is a different component. And each unit is an entity, so it has a unique ID, and it has potentially those 3 components, maybe more, maybe less. That's the reality. So that's the components, and that's the transform / systems. I think I need to update one of the subtitles on this. So the efficiency basically comes from breaking objects into components and then storing them in dense arrays, so we optimize the memory bandwidth associated with reading and writing them. And the rest of the talk, and the original point of my talk, was how do we implement it, which now is more like a nice thing to learn, but I think the main takeaway you should have has already been given. But we can still continue and talk about implementation a bit, because I haven't shown much code yet. So actually, there's no code, it's mostly diagrams. But I will explain to you how you can do something like that, because again, I think the main point is, okay, that sounds interesting. I would like to optimize the memory bandwidth for my program when I go home. But maybe I don't want to use or I cannot use an ECS system entirely, or I think it's too much. But maybe I could just take the data structure. So let's look at how it's done. What's the goal? What are we trying to achieve? What are the constraints? And also the constraints are important because they help you figure out, can it work in my case or not? Because games have their own demands and their own necessities. You might not work for whatever you're doing. So obviously the thing we're optimizing the most and the thing we want is that if we're iterating for components, we want it to be as fast as possible, as fast as the machine is basically allowing us to do it. So mostly speaking, it is like make as best use of the memory as you can to make sure we don't waste memory bandwidth, cache utilization, etc., etc. So yeah, basically, it should be as fast as going through an array that doesn't have any unrelated data. If we start doing tuples, for example, like our update position use component tuples, right? Because it takes all the position and all the velocities, so it's technically a tuple of both. We would like to be very fast. We can't guarantee that we will be as fast because it's a problem that gets infinite complexity eventually. But I want to try to do, if I want to do a zip iteration over like a selection of components, I want it to be pretty fast. Extremely fast would be nice, but most of the time, due to implementation concerns, you can only go as good as pretty fast or very fast. You can try to constrain the tuples at creation, saying, okay, like only those combinations of components will actually be used, and then your data storage can try to optimize for those cases. But it's a vast field, and I don't have all the time in the world to explain why. But trust me on the fact that it is a complex problem, and it kind of runs into like a combinatorial explosion issue eventually. We want a fast lookup. So for example, if I have a given entity and I want to display on the screen either for debugging purposes or just like to give the player feedback or whatever else, I want to be relatively fast in getting all the components it has. By which I mean, like, I think a linear search will be considered too expensive. I won't want to have to go through every component table and say, do you have entity X? Yes, I know because I actually did like a linear search for the array. I want something faster. So I need some form of an index or a lookup table that will allow me to be able to do a lookup in reasonable time. That's a thing that not everybody does, but for example, my games sometimes need it. Sometimes I need to be able to iterate through components in a deterministic order. And by deterministic, I mean if I start the game, I start deleting and adding components all the time because some units are created and deleted. I want a way to guarantee that if two players on two computers are iterating through the same collection, I get the same order. It's mostly used for multiplayer synchronicity and things like that, but it is a use case that is not always used by every game, but I would say, I don't have a number, but a solid class of video games and the way they handle their simulation requires sometime that they have to be able to iterate through all the components through a deterministic order. It doesn't have to be by like increasing index, but it has to be deterministic. Regardless of like how many items have been deleted, even if someone like hot joins the game or whatever, and gets like a copy of the current state and doesn't have to repack a bunch of data, it still should get the same order. And of course, entity ID should be stable upon creation and deletion. So if I add or remove components or add or remove entities, all the other ones I can still do a lookup by ID and I still find my babies. I don't have to. I will not lose them. So I looked a bit at some systems. So I've done some checking. Unity Engine has been offering like an ECS system since 2018. I think this is the big spike you see in the Google trend that I showed earlier. They made like a big deal of the fact that Unity Engine was going to do an ECS system in the future in 2018. They had a cool demo called the Mega City. There's an interesting talk behind it about how they did it. It's a nice watch. I recommend it. I also get ENTT, or Entity, I'm not sure how it's supposed to be pronounced, which is an open source one. You can find it on the internet. It's C++, unlike Unity with C#. Well, and internally C++, but C# as the API. I think it's used, some parts of Minecraft are using it, which I included because that's one of the difficulties I had during this talk was finding actual production use cases of ECS, because game developers love to tell other game developers that they should use an ECS to solve all their problems, but when you ask them, okay, which ECS are you using? Like, we're not really doing ECS, but so yeah. And Flex is the one that I looked at because it has been used in some bits of our engine, but it's in C, so I hate it, and I refuse to take a look more than that because it's C. I just don't respect that. This is a C++ conference after all, so you know, let's focus on the important bits. Oh, and that's the wait, but my transition is broken. Okay, fine. We can move to the next slide. So. Okay, now I will just, how much time do I still have? Okay, 15 minutes. I'll just show you very basics. How can you implement like the most simple data structure that will allow you to do like those kind of magic vectors including the constraints we have. Because as I mentioned before, the constraints we have do not allow us to just use a vector. Just like a simple vector would not be good enough, because as everybody knows, if you delete an element in the middle of a vector, you have to move everything around, which means that suddenly you can't find your babies, or you have holes in the section, either you leave a hole, but that's bad because then you need to skip some bits, and then you don't have the most packed data structure ever, or you don't, and if you shuffle data around, then your keys starts getting jumbled and you can't look up things. So that's the problem we're trying to solve, right? So some people have tried to make solution for this. If you ever heard about a paper about Colony or Hive, they keep changing the name. I don't think it's been standardized yet, but it's been in discussion for a bit. It's a data structure that tries to address the problem by having what they call skip fields, which is either a bit set or some metadata that basically allows you to jump across gaps in a vector. So it's a vector, and when you remove an element, instead of repacking everything, you just mark it as dead, and then you have, the whole thing is about having optimization to know how to jump through it when you iterate. It's pretty good, but it still wastes memory because it's not densely packed. And I think there are simpler ways to do things. And to me, the simple way, and the one I want to focus on, this is the one that entity does, for example, is just swap, every time you have to delete something, just swap it to tail, just swap it with the last element, and then have an external index. Because again, like the thing we're trying to optimize most, and again, that's one of the main points here, is that we're trying to optimize the most is iteration. Lookup doesn't have to be 100% as fast, it has to be fast enough. So having an external table that does the lookup for us and gives us the guaranteed, like, not iterator, but index stability is good enough. So how would we do it? So yeah, that's what I was saying here. I can just skip that bit. Okay, cool. So, let's skip this. Okay, so here's how that works. I don't have a name for this, and this is the thing that sparked my talk already, because I ran into this data structure looking at how ECS are implemented. I couldn't find a good name, so you tell me if you've ever heard about this, or at least the concept. I don't know about the name. The guy who was mentioning it was the author of Entity. He has an interesting blog about how he implements the whole thing and how data structure should work with it. I think he called it the dense/sparse array, or the dense array sparse index. It has different names. But the whole idea is, when you start, you just have an array of all the components. So A, B, C, D, E, F, G is just like instances of the same component, right? I just try to give them letters so not to confuse you with ID. At the bottom, you have an index lookup that is just an offset. It basically say, okay, if I want entity 0, it's at index 0 in the table. If I want entity 1, it's at index 1, etc. When you start, when you just keep inserting, that's very simple and consistent, right? You just, this is the actual ID. This is the index of that ID in the table. That's as simple as it is. If I want to start deleting something, then this is where I start doing some things. So like, I want to delete B, for example. B is dead, that my unit B is gone forever, RIP, and I'm trying to delete it. So I want to keep the thing at the top completely packed. So what I will do first is I will mark this entity as dead. One of the classic options is to just do a -1. So if someone tries to look up entity 1, you just get like, not there anymore, bro. You're going to have to do something else. And then I swap it with the last one, because I want to keep that one, the top one, packed. And of course then, wait, did I do that? Oh yeah. And then I have to update this index, because obviously now this entity number 6 is not at offset 6, it's at offset 1. So I just update the index, and that's it. That's all I have to do. So it's not. Well, first of all, there is no most of the time there's no reallocation. It's just like a pushback, and no, it's not even a pushback. It's just a swap. Like it's one memory swap and 2 memory writes, and that's it. And that's how I can delete something. And I still keep my top array like packed. So if I iterate over it, again, not deterministic order anymore, because I start jumbling things around. But I have all my entities super packed, and I'm not wasting any memory bandwidth when I iterate over it when my actual cost is. One of the assumptions is, of course, that iteration is more important than addition, than adding and deleting stuff. In general, I mean, if you're trying to optimize for, if you optimize for insertion and deletion, you're probably not going to have your main issue is not iteration, right? But in video games and in many things we have, the problem is not creating new things, it's iterating over them. And then we try to just make creating new ones not as painful as it could be. Now, if I want to insert a new one, well, obviously I just put it at the back because that's the only place I can insert new elements because it's always a dense array. And then I will just push back a new index entry and just say, oh, this is where your thing is. And that's it. That's really the data structure. It's really simple. I haven't seen any papers about standardizing anything similar that I could talk about. And again, I don't claim to have invented this. I just found it by looking at the blog of Entity and how it's implemented. And it's just 2 arrays. It is just 2 arrays, and that gives you good enough things to make sure that that satisfies all the constraints we have. With one exception. We talked about lookup before. There's one case here that is not satisfied, and it's the reverse lookup. If I have like a component and I want to know what its ID is, I can't, right? There's no easy way for me to get it from there, because unless you want every component to keep an index of itself, which again is wasting memory most of the time, that is not worth it. I can't really reverse it from any of those indexes without a linear search, which is not good. So the solution would be, if I really need that, which in some cases you do, so like, okay, I have a given component, but I lost where it's coming from. I lost its entity ID. Well, what I could do is just, okay, let's keep a number. Like, this is basically the data I want, right? This is number 0, this is number 6, this is number 2, 3, 4, 5, 7, etc. But I don't want to store it in there. So what I'll do is I'll do the exact same thing that I keep doing. I'll just put it in another array. And that array shares the same index keys as the top one. So if I'm given like entity G, component G, I compute his index. It's pointer arithmetic, but it's just arithmetic, right? It's like, okay, it's basically start distance from the start to it, which gives me 1. And then I just take that index in this one at the top, and that's my thing. And that's just 2 memory lookups. There's no linear search. It's arguably constant time, but again, complexity, you've noticed I haven't talked about complexity at all in this talk. It's because complexity is important, but memory latency is starting to get more important in some cases. It's not 100%, I'm not gonna say it's fine, as long as you have good data locality, go nuts and use like factorial or whatever, polynomial like time. No, don't. Try to keep it to constant or linear, but there are many cases where actually memory latency is a bigger problem than the fact that your thing is linear rather than constant. Or maybe not constant, but logarithmic is a big one. I haven't had any slide about it because, again, I had to fit this slide and this talk in 1 hour. But one of the big things that people have started noticing is that binary search is starting to get slower than linear search in some cases, because it keeps jumping through memory all the time. And on top of that, we have this thing called branch prediction, which also hates when you randomly jumps left or right all the time. And at some time, doing the dumb thing turns out to be faster. And that's it. That's if you really need to be able to keep your indexes back, but you don't want to poison your actual component data, you can just add a third array. And then you're back to be able to have the relationship both way between indices and components. So yeah, it's as easy as 2 or 3 array, and it's simple enough to implement. Maybe it's not standardized. I would say it's not standardized because it's too easy to write. Is a bad argument, because some people would argue that implementing vector is not that hard, and still I'd rather have it than having to implement it myself. So I don't know. The second array can be split into pages, because one of the issues you can run into is that you start having like big gaps in your indexes, because this one will always be packed. This one will always be packed. You will always be paying as much memory as the number of active components. But this one, well, you notice that we start putting like some -1s when we kill some things, and it's just gonna keep growing and growing and growing, unless I implement some form of like reuse of IDs, which is also a big important thing. But again, see me after, or I'll probably make a blog post about it. If you don't know this man is Fermat. He's very well known for having like a last theorem of Fermat, which he famously, in the paper that he wrote in the 1600s, said, oh, I have a proof for this, but it doesn't fit in the margin of my paper, so don't worry about it, trust me, I'll tell you later. And he never wrote it, and it was proven 350 years later or something using computers, and nobody thinks that his proof actually worked. But that's the idea. Like, see me after, I can explain to you how to implement ID reuse and things like that, which is usually a thing you want to do. Else your index lookup table might start growing crazy, even if you have only 5 items in it, because you created and deleted a million entities, and you usually want to avoid that. Do I even have time for the multi-component case? I think I would rather take questions, so I will skip that bit and go to the conclusion. There we go. Sorry, I have to skip over a few slides. There we go. Okay, so did it solve all our problems? Is, I guess, a question, right? So again, production games at PDS do not use ECS. Like as far as I know, no game in production at Paradox uses ECS so far. Future titles, I've been looking at potential uses. As I said, our engine team has been experimenting with Flex for some animation system, I think. But it's still very much an experimentation, and I don't know if we will keep it or not, or write our own. And in the end, if it's used by only one system, maybe it's not really ECS. Maybe you just have those nice dense arrays, and that's it. And yeah, for gameplay, I'm still looking for it. If you're a game developer and you actually use ECS at scale with like, I don't know, 100 different concepts or components, and you actually manage to use an ECS framework from that, I'm really curious how you did it. Because every time I try to ask, people are like, we tried. Yeah, we can skip that. So yeah, one of the issues that you run into this, and that is somewhat important, is that you kind of want to tie down like which kind of component pairs you can have, tuples. They're called archetypes in some literature. An archetype is basically an entity that is guaranteed to have like a select set of components, and that's usually the one you want to operate about on a given transform. Designers hate them, especially if they're pinned in code. Because what designers love, especially in like complex games that have lots of systems that interact with each other, is they like to say, oh, what if suddenly the unit system was starting to feed data from the spy system, because that would be super cool. And then you're like, oh, but you can't access the data here because I have to change the archetype and make sure that every of those has access to this component, and that changes the whole lot, blah, 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 blah. And this is a thing we started noticing when we tried to use a similar approach, but it was mostly for multi-threading at the time, not for see my other talk, I guess. They really hated the fact that nowadays system updates are like taking a very well-defined sets of components in the signature. They really like to be able to do unit.get or .access whatever, and then just jam a gameplay feature like 5 minutes and be able to test it. So like, that's cool. I could do it. And now they're like, oh, I can't do that. Now I have to go back to the caller, change the signature, add one new component to this update, and now I get warnings that this is... They don't like it as much. So there is limits to this. But the speed up is very important. And again, the fact that if you start defining your updates as free functions that take constrained input by a type will allow you to get multi-threading for free and decoupling. So I could have called this talk like, I use ECS and it didn't solve any of my problems. But it's not entirely true. I think it is important to realize why we went there, because of the data-oriented concepts and all the speed-ups that it can go. If you start having multiple components and you want to make a zip view iteration, it starts getting a bit tricky. That's the bit I skipped because this talk was complex enough. But again, single components is the structure I showed you. I think it took like 5 minutes to explain, maybe 10. I don't think it's really hard, 2 or 3 vectors, and you will get something out of it. So yeah, consider the dense parse array. It's the fastest and ordered iteration speed you can do, basically. And it still keeps constants outside of relocations, obviously, if you run out of memory in your vectors. But outside of relocation, it's constant insertion and deletion time, because it's just swap or push back. It's constant lookup by ID, because you just look for an indirection table. It has ID stability, but not pointer stability. Obviously, if you insert or delete, the memory address of a given component changes. But the ID is stable. You can just do an extra lookup and find it again. And it has okay, but not amazing deterministic iteration speed. Because usually what you do if you want deterministic iteration is you go through the lookup array, basically, because that one is guaranteed to have like an index, and you do a memory jump. So it's not as good because you keep jumping through memory, but if it's packed enough, you might not pay a cost that is too high. And also, like, yeah, it mostly works, and I did not mention that before, it mostly works with trivially relocatable types. So like types that do not like have pointers to themselves or funny things like that. It's just things that you can mem copy. And again, I think this is a reaction thing that I've heard more and more in the C++ communities. People going more and more to like dumb structs that you can just mem copy everywhere. Because you get a lot of places where you have huge gains by the fact that the thing can just be mem copied and then forgotten about. Right, so decouple your data is basically the one thing I want you to take home. It's good for multi-threading, it's good for cache performance. ECS is probably overkill, But try to take a look at data structures that have spawned through the systems, because there is something there that can probably be taken and used in your own projects. Oh, and furthermore, I think your build should be destroyed as usual. Thanks. I have some references if you are interested. There's the collection from Michele Caini on ECS is pretty good. There's the GitHub of the project, and he has made a talk, I think, in Italian C++ or something like that, where he compares his ECS to like Unity, and he talks more about the implementation if you're interested in that stuff. I'm probably too late for questions, but I don't know, if we're not getting kicked out, I can still maybe take one or two. Especially if you use ECS and it solves all your problems, I'm interested.
Hey.
Hello.
Hi. I've been trying to use the ECS ever since I heard about it. I think it was Mike Acton's talk or something.
Yes, that's the one that's often mentioned.
I mean, I immediately fail at the first thing, because the very basic example always is about position. And how do you do hierarchical position? Because that's my biggest pet peeve with this.
Yes, because ECS do not give you any cap of hierarchies, right? So, for example, the classic is people would like to put them in like quad trees or oct trees or blah, blah, blah. Have you seen his talk about the megacity in Unity?
I did not know.
Because he talks about it, and he talks about how he managed to solve some of that hierarchical data, not by introducing a new structure, but by taking advantage of the fact that the way this is stored is hierarchical. So basically having intermediary steps where you can basically skip over chunks of the object. And I think the way it's done is that it probably keeps components into either different sets, or at least sets that are together in memory. So you can't use the sparse thing because it keeps jumbling things around. But it can take advantage of the fact that this array, you can basically do a jump like over 1,000 entities, because you know that the first 1,000 are this block, then the next 1,000 are in this cell, etc., etc., etc. But yeah, I think it's called like Mega City Unity thing. It's a 30-minute talk. It's pretty insightful.
Cool, thanks.
You said that the ECS concept is not that much applicable onto maps. Did you still explore the performance benefits if you try to build a map or / dictionary structure?
The thing about maps is that there's only, actually like standard maps, there's only bad ways to make them in memory, right? Because it's going to be a red-black tree. That's basically the standard kind of force. It doesn't tell you it's a red-black tree, but if you look at the requirement, it is a red-black tree. And it's a tree, which means it's a list, which means you're jumping pointers all the time, which means there is no way you can guarantee data locality. The best you can do is try to chug an allocator next to your map and try to get the poor man's version of data locality, because every item in the map will hopefully be close enough in the same memory chunks. But you're still jumping through memory, and you can't guarantee that you're going to that two elements are actually next to each other. They're guaranteed to be in the same map, which is better than what map does, but it's still very far away. And that's why, if you have looked at hash tables, for example, that's why people keep telling do not use an ordered map in the standard, because an ordered map also has to be what they call buckets with lists. Like they can't use what we call open addressing. And open address hashes, I'm getting a bit far away from the topic, but hash maps, they always, if you don't follow the standards, to implement them as one array with only a few gaps in it. And it's okay enough for iteration, because you just have to skip a bunch of. It's kind of equivalent. It's not as good as Colony in terms of skip fields, but it is still, you have the guarantee that you're going through an array. So as long as your hash map is reasonably populated, like let's say 75% or something, you're not wasting too much memory when you're doing when you're doing fetches. Although arguably you will still be fetching keys and a bunch of things that you don't care about for your actual update. So it is okay, but I think this misses the point of just saying, no, we want a vector of things, and this is the only thing that I'm going to fetch.
Yeah. Okay, thank you.
Do we have any more questions? Okay, so we're done. You can come and ask me afterwards, and I will happily answer anything else.